Hey, thank you everyone for being here today. So basically the purpose of my work is to try and understand the health effects caused by exposure to lunar dust. And so in order to do that, we have to acquire better lunar regolith simulants than what we currently have now. And we have to do that because acquiring real pristine lunar samples is very difficult, especially in the quantities that we need in order to do our our studies. So basically what I'm doing is I'm taking JSC1A, which is a lunar regolith simulant, and I'm trying to improve it in order to be able to do reactivity and cell toxicity studies in order to be able to see how these samples might affect people. And we need a lot of it in order to do multiple studies. And so what we do is we take the JSC1A and we use a simple reduction method described by Allen et al. 1994. And then what we do later is we measure the reactivity or the OH radical generation. I'll talk a little bit about that later, of both the reduced and non-reduced JSC1A. And I also present a little bit of data regarding the cell death caused by reduced and non-reduced JSC1A. And so we're starting with JSC1A because it's very widely available. So JSC1A was developed in order to aid in engineering and resource utilization projects related to lunar exploration. It was supposed to simulate the Mare basalts, but it doesn't do a very good job of that. And so, but there are positives and negatives with JSC1A. So some of the positives are that the grain size, or the angularity, grain size, the specific gravity, and the glass content are pretty much on par with lunar regolith. The electrical and thermal properties also match up pretty well with lunar regolith, so it's really good for engineering applications like rover testing. But there are, of course, downsides to JSC1A, primarily regarding the mineralogy and the chemistry of it. So there's a fair amount of clay minerals present in JSC1A, and since there's no aqueous alteration on the moon, you wouldn't see any clay minerals present in actual lunar regolith. There's also a large proportion of oxidized iron in JSC1A, whereas in lunar regolith, you either have Fe2 plus or Fe0. And the biggest drawbacks are that there's no agglutinated glass or metallic iron present in JSC1A, whereas it's very common among actual lunar regolith. And so what we do to try and make JSC1A a little bit better is we try and reduce it. So we're trying to add metallic iron to the surface of JSC1A. And so what we do is we take about 3 grams of it, we add it into a glass sway boat, and we add it around there in the middle of that silica tube. And then we put that into this furnace right here, and then we heat it for 15 minutes at 900 degrees C. So when that's done, we let it cool down, we remove the JSC1A, and then the first thing we notice is that it gets darker, and this is due to the formation of metallic iron on the surface. And we repeated this a total of 3 times on 3 separate occasions. And this is what we got. And so basically these are all just JSC1A grains all over, and these blue arrows are pointing towards iron metal blebs on the surfaces of these grains. And this is very similar to what they observed in that Allen et al. 1994 paper. So we were able to successfully reduce JSC1A and add some metallic iron to the surface, as is common among the lunar regolith. It's a common characteristic among lunar regolith. And so after that, what we do is we measure the OH radical generation, or the reactivity of our reduced samples, and our non-reduced as well. And the reason we look at OH radicals because it's known to be hazardous to biological species, and so it's important to measure the OH radical generation of our samples. So the way we do that is we use a technique called electron paramagnetic resonance spectroscopy, or EPR spectroscopy. And so what we do is we take about 200 milligrams of JSC1A, and then we incubate it using a inorganic molecule called DMPO, and that will trap any of the OH radical that is made by the JSC1A. And then what it does is that it forms this stable compound that can then be measured by the EPR, because the OH radical cannot be measured by itself. It has to be attached to something more stable. And so what we got out of it was the results on the next page is that reduced JSC1A is way more reactive compared to non-reduced JSC1A. So here on the y-axis, we have the amount of OH radical being generated. For the non-reduced sample, we're only making about 1.8 micromoles of OH radical, whereas for the reduced, we're making double that. We're making about 4. So it seems that heat treatment and reduction of JSC1A and the formation of the metallic iron on the surface is leading to much greater reactivity compared to non-reduced JSC1A. And here we have the same two graphs here on the right, but now we're comparing it to some pure mineral phases that are found on the lunar surface. So here we have olivine, augite, and labradorite. So that's part of an early project I did a couple of years ago, where I looked at various pure mineral phases and tried to measure the OH radical generation potential of each of them. And so it seems that reduction of the JSC1A and the formation of that metallic iron causes a huge spike in reactivity, even compared to some of these iron-rich silicates that are commonly found on the lunar surface. And in that work, we found that iron-rich silicates are the most reactive minerals compared to pretty much anything else. And so here we have some data obtained from our colleagues in the Department of Pharmacology. And so basically what they found is that here we have our JSC1A that's not reduced, and here we have our reduced JSC1A. And so the y-axis is the number of cells that have been counted after a treatment. So we have here our control. And for our non-reduced JSC1A, they counted about 100 cells. And for the reduced, they counted around 50. So it seems that the heat treatment and reduction, again, is not only leading to huge increases in the reactivity, but in the toxicity as well. So here's some results presented by Wallace et al. 2010. And so here what they did, so first we're going to focus on the graph on the right, or on the left, excuse me. And what they did is that they measured the reactivity of a nanophase iron simulant represented by this black bar right here. And they measured it with one of their batches of JSC1A, represented by this gray bar. And this little bar over here is amorphous silica, so the silica that they used in this sample, but without the nanophase iron. So it seems that the presence of this nanophase metallic iron is leading to huge increases in reactivity. Unfortunately, they didn't measure anything quantitatively. They just did everything in arbitrary units. And so something that we can do that's pretty interesting is we can then compare to our results. And so basically, if we were able to plot our JSC1A here, it would come out to somewhere around here. And the reason we can say that is because their JSC1A came out to around 2,500. And if the reactivity of our JSC1A doubled due to reduction, then that means if we were to plot ours on here, it would be around 5,000. And so on this graph on the right, so this is also work that they did, our JSC1A would plot around here. And so as you can see, these are all Apollo 16 samples. So our reduced JSC1A so far seems to mimic the reactivity that of Apollo 16 samples. And so this kind of shows sort of the work that needs to be done in order to improve or to continue to improve a JSC1A, because since JSC1A is supposed to be a MARE simulant, this should come out higher. It should come out up here with all the other MARE samples. And it's not. It's coming out around here, so it kind of just shows that there's still more work to be done. And so for our conclusions, we were able to take JSC1A and successfully reduce it and add metallic iron to the surface of it, just like they did in Allen et al. 1994. So we were able to do multiple hydroxyl radical measurements with little errors, so we're pretty confident that our methods for measuring the reactivity are pretty good. And we found that reduction of JSC1A adding this metallic iron to the surface causes the reactivity to double compared to that of non-reduced JSC1A. And it also seems that metallic iron leads to significantly larger cell death compared to non-reduced JSC1A. So this has a lot of implications in terms of lunar dust, since lunar dust has a lot of metallic iron present in it. And we also found that reduced JSC1A with metallic iron, again, generates a lot more hydroxyl radicals, much more reactive compared to minerals like olivine and augite. So for future work, what we want to do is we want to take these methods and be able to use them on other samples. And so we want to take something, say, like, let's take olivine and let's reduce it, and then let's test how reactive and toxic it is, and then let's compare those results to the Wallace et al. 2010 work and see how well it matches up with actual Apollo samples. And something we also want to do, too, is we want to see what effect heat treatment alone has on these samples besides just the reduction. So let's remove the H2, and let's add something like argon, and let's see how the reactivity and toxicity might change with just heat treatment alone. And something we would also like to do, too, is we like to add or try to obtain this nanophase iron simulant and try to, let me go back real quick, and then try and maybe get some similar data to what they have here and maybe change this y-axis from arbitrary units to actual OH radical generation, and then we can then more effectively compare to what they got over here for the reactivity of actual Apollo samples. And with that, I'd like to thank all these great people, and I'll take any questions you may have. A lot of questions, sure.
Have questions?
No, there's too many people.
I have a question for you, but I'm going to wait for the public. I saw your hand going first. So.
Okay, Dan Britt, University of Central Florida. I can tell you why your reduced sample got closer to the highlands soils than the Mare soils is because the San Francisco the volcanic suite that you got for JSC1 is actually erupted in a continental area and is way more feldspar rich than what you're going to find for Mare samples. The real question I have is why use JSC1A at all?
So
there are much better simulants that are a lot closer to lunar mineralogies that aren't full of for things like calcium, which you don't really want and might affect your reactivity.
Yeah, so we started with JSC1A first just because like that's kind of what we had to start with, but we definitely want to go beyond JSC1A.
Well, if you'd like a free kilo of much better simulant, give me a call.
Sure, yes, we were definitely considering doing that for sure for our next step.
The first one's free, yeah.
I also wanted to just give a plug for another collaborators that we work with who make their own lunar simulants. They're kind of non-NASA, and they have a Mare simulant and a Highland simulant, both of which include agglutinates. Their physical characteristics are much more realistic. So if you'd like to chat, I could give you their contact information. Yeah. They would also love to be on your list of
yeah, definitely.
Regolith
No,
simulant,
if you guys have
sources. Things
that are better, definitely. I'd love to get a hold of it.
We have time for one more question. Just one more. No? Yep. That's okay. It's your question.
I think I know the answer, but what relevance does heating these samples to 900 degrees Celsius have to the surface of the moon? And is the nanophase iron that you're forming anywhere near the abundances that you would actually find in the lunar soil?
So the abundances, we don't have a clear answer on that yet. I want to try and get Mossbauer measurements on these and try and see if the amount of metallic iron is adequate. I'm sorry, what was your first part? That question?
Why? I mean, the lunar surface is heated in 900.
Oh, okay. No. So basically, our main goal with that is to try and get the metallic iron. We're not trying to really replicate the actual like vaporization and the formation of the agglutinates. We're trying just to get the metallic iron to see what effect metallic iron alone has on the reactivity and toxicity.